Welcome to section 6.1, Substitution and Elimination. Let's start off with an example. Okay. So our example here is about movie theater ticket sales. So a movie theater sells tickets for $15 each, with senior receiving a discount of $5. One evening, the theater had $3,555 in revenue. If X represents the number of tickets sold at $15 and Y the number of tickets sold at the discount price of $10, write an equation that relates these variables. Okay. So right off the bat, we know that we're going to have a variable X that represents the number of ticket sales sold at $15 and another variable Y, which is the number of ticket sales sold at the discount price of $10. Okay, so we have two variables. We know that movie theater sells tickets for $15. Okay, and seniors receiving a discount of $5. And one evening, the theater had a revenue of $3,555. Okay, so we want an equation that relates all of these variables. So we're going to let X represent the number of tickets sold at $15. And we're going to let Y represent the number of tickets sold at the discount price of $10. Okay. Now we know that the tickets cost $15, so that's the regular price. So the total cost of tickets at $15 would be 15x. So this is the cost, total cost. Let me write that in there. Total cost. I'll rewrite it for us. That'll be the total cost of tickets. The total cost of tickets. And then the total cost of the discount tickets at $10 would be 10y. So this is the total cost of discount tickets. Discount tickets. Okay. So we know that the theater had revenue one night of $3,555. So to write an equation that represents that revenue, we would take 15x plus 10y equals 3,550. Okay, so we'll take the total cost of the regular tickets and the total cost of the discounted tickets, or the senior tickets, and we would add those together to get our revenue cost. Now, suppose in this example, we also know that 253 tickets were sold that evening. We can write a second equation relating X and Y, and then group the two equations together to form a system. So the additional piece of information given was that 253 tickets were sold. So we know X represents the number of tickets sold at $15 and Y represents the number of tickets sold at $10. So the total amount would equal the 253 tickets. Okay. So to put the two equations together, we'll draw our brace here, and then we will write our first equation, 15x plus 10y equals 3,555, and then x plus y equals 253. So this would be considered our system of equations. So the definition of system of equations is a collection of two or more equations containing one or more variables. So in our previous problem here, we had two equations that we put into a system, and we have two variables in our system, x and y. So when we put them together, we create a system of equations. For these examples, we're asked to describe each of the following systems. So for A here, we have two equations, equation 1 and equation 2, and we have variables x and y. So let's say two equations and our variables are x and y. For B, we also have two equations, and our variables that are present are also x and y. Okay. For C, we now have three equations, 1, 2, and 3. And with these three equations, we have three variables that are present. So we have x, y, and z. Okay. For D, we have two equations, just 1 and 2. And our variables, we have three. So we have x, y, and z. And for E, we have four equations, and we have three variables, x, y, and z. Okay. So just to keep in mind moving forward, when you see a brace, that's usually used to show that we are working with a system of equations. So the brace is this little bracket here, okay, that usually signifies we're working with a system of equations. And then when you are working with a system of equations, it's best to number each equation in the system so that you can easily reference it as you are solving your system of equations. So in each of these systems, you see here that each equation is labeled 1, 2, 3, 4, and so on. That allows us to identify the equation that we're going to work with as we try to solve the system. So a solution of a system of equations consists of values for the variables that are solutions of each system of each equation of the system. So to solve a system of equations means to find all solutions of the system. So in these next 2 or 3 examples, we are asked to identify a solution to a system of equations. So we're going to be given an x coordinate and a y coordinate, and we have to determine if it is a solution to the system. In order for it to be a solution to the system, it has to satisfy each equation of the system, meaning it has to make the equation true. So when we substitute in the x coordinate and the y coordinate, it must make the statement true. So for our first one, we need to show that x1 and y -4 is a solution to the system. Okay, so we will substitute in 1 for y and one for x, and -4 for y. And we want to know if this is true, so we will get 3 plus 4, which equals 7. So that's true. Then we'll take the next equation, substitute in 1, substitute in -4. So that would be -1 minus 8, which equals -9. Okay, so when we plugged in these coordinates, we got 7 and we got -9, which are the same values that we got in our system. Therefore, we can say that the point 1, -4 is a solution to this system. Let's do the next one. We're going to show that x equals 4 and y equals 1 is a solution to the system. So we'll substitute in 4 for x and 1 for y. So that would be 4 minus 1, which equals 3. We'll do the next one as well. 4, that's plus 3 times 1, so 16 plus 3 is 19. Those values are the same values in our system, so we know the point 4, 1 is a solution to our system. Okay. Let's do a 3-equation system. So now we're going to show that x equals 3, y equals 2, and z equals 1 is a solution to the system. So substituting in 3, substituting in 2, and substituting in 1. All right, we will get 5 minus 1, which is 4, so that is the same. Then we will substitute in these values in the next equation. So plus 5 times 1, so that will be 6 minus 2 plus 5, which will get us 4 plus 5, which gets us 9, and that is the same. Then the last one, we have 3 minus 2 plus 1. So that is 1 plus 1, which equals 2, and that is also the same. So we know this triple ordered pair is 3, 2, 1 is a solution to our system. Okay. So when a system of equations has at least one solution, it is said to be consistent. When a system of equations has no solution, it is said to be inconsistent. If each equation in a system of equations is linear, we have a system of linear equations. Okay. The problem of solving a system of linear equations in two variables can be viewed as a geometry problem. The graph of each equation in the system is a line. So, a system of two linear equations containing two variables represents a pair of lines. The lines may intersect, be parallel, or be coincident. That is identical. In considering each situation, take note of the number of intersection points. When solving systems of linear equations in two variables graphically, we are looking for the intersection points of the graphs. So here visually, we have are three different types of solutions where we could have an intersection. This is where our system has one solution. We could have parallel lines. This is where our system has no solution because parallel lines do not cross. And for the third one, this is where we have identical lines. So the two lines or two equations in our system are the same exact line. Therefore, we have an infinitely many solutions. For this example, we're asked to graph the system of linear equations. Our first equation in our system is 3x minus y equals 7. Our second equation is negative 2x plus 3y equals negative 7. So to help us graph this system of linear equations, we are going to write each equation in slope-intercept form. So for equation 1, we'll take 3x minus y equals 7. The goal is to get y all by itself. So we will subtract 3x to the right side. Then we will divide all terms by negative 1. And this then gives us our equation y equals 3x minus 7. From this equation, I know my slope is 3, and I know my y-intercept is negative 7. Okay. So my slope is 3, my y-intercept is negative 7. So that means I'm going to have a point down here at negative 7. My slope is 3, so I'll be going up 3 and over 1. So up 3 over 1. Up 3 over 1. Up 3 over 1. And then I can connect my dots. Okay, and that is equation 1. For equation 2, we're starting off with negative 2x plus 3y equals negative 7. I'm going to add 2x to both sides, then divide everything by 3. So all terms by 3. Okay. So I now have my slope-intercept form where my slope is 2/3 and my y-intercept is negative 7 over 3. Y-intercept B is negative 7 over 3, which is roughly negative 2 1/3. So that is right here. Okay. Then our slope is 2 over 3, so that's rise over run. So I'm going to rise 2 and then run 3. So rise 2, 1, 2, and run 3, 1, 2, 3. Then I'm going to rise 2, 1, 2, and run 3, 1, 2, 3. Okay. Then I'm going to connect my dots. And that is the line for equation number 2. So our intersection point is going to be our solution, and that is the intersection point 2, negative 1. Okay. All right. Objective 1, solving the system of equations by substitution. So most of the time we use algebraic methods to obtain exact solutions. A number of methods are available for solving systems of linear equations algebraically. We will introduce 2 methods, the substitution method and the elimination method. We will first start off with the substitution method. So in this example, we're asked to solve this system of linear equations by substitution. Okay, so we have our system. We have equation 1 and equation 2. Okay, this is the same system that we use to graph. So we solved it graphically. Now we're going to solve it using substitution. And we're going to walk through these 5 steps. So for step number 1, we're going to pick one of the equations and solve for one variable in terms of the remaining variables. Now, you can choose either equation, 1 or 2. I recommend going for the equation whose variable has a 1 or a negative 1, or whose variable has a coefficient that is a lower value. So I am going to take equation number 1, 3x minus y equals 7, because our y variable has a coefficient that's negative 1. And I'm now going to solve for y, because I'm going to solve for one variable in terms of the other. So I'll have negative y equals negative 3x plus 7, and then y equals 3x minus 7. Okay. Now for step 2, we're going to substitute the result into the remaining equation. So now I'm going to take the equation that I found, or I simplified to, or rearranged to, and I'm going to substitute that into the equation that I did not use. So that would be equation 2. So negative 2x plus 3y equals negative 7. So I'm going to take this equation of y and substitute it in. So y equals 3x minus 7. So now my equation 2 looks like negative 2x plus 3 times 3x minus 7 equals negative 7. Okay. So now let us distribute that 3. So we have negative 2x plus 9x minus 21 equals negative 7. Okay. So for step 3, if one equation and one variable results, solve this equation. Otherwise, repeat steps 1 and 2 until a single equation with one variable remains. So we want to now solve our equation all the way down to one variable. So, in other words, what does x equal? So we'll simplify. 7x minus 21 equals negative 7. Add 21 to both sides. Divide by 7. And so now x equals 2. Okay. So for step 4, we're going to find the values of the remaining variables by back substitution. So remember, in step number 1, we got our equation for y. So we know y equals 3x minus 7, but this originated from the equation 3x minus y equals 7. So that would be the equation we actually want to use. So you want to use one of the equations from the original system of equations in order to find your other values. So we're going to use equation number 1, 3x minus y equals 7. And I'm now going to substitute 2 in for x so that I can find y. So now I have 6x minus y equals 7. So minus y equals 1. So y equals negative 1. Okay. So I have x equals 2 and y equals negative 1. Well, I know these are the solutions because I already graphed the system and I found these same coordinates as my solution. But algebraically, we can now substitute in this x coordinate and y coordinate to determine whether they are actually solutions. So our original system was 3x minus y equals 7, and negative 2x plus 3y equals negative 7. So I'm now going to substitute in 2 for x and negative 1 for y to see if they are solutions to my system. So I'll have 6 plus 1, that equals 7. And I'll have negative 4 minus 3, equals negative 7. And we see here that it makes our statements true. So our solution is the ordered pair 2, negative 1. And that is how you solve a system of linear equations by substitution. All right. Now our second method, elimination. Okay, so this method is preferred if substitution leads to fractions or if the system contains more than two variables. Then I would recommend you use this method called the elimination method. So the idea behind the method of elimination is to replace the original system of equations by an equivalent system so that adding two of the equations eliminates a variable. So the rules for obtaining an equivalent system of equations, you need to interchange any two equations. Okay. Then you want to multiply or divide both sides of an equation by the same non-zero constant. Okay. And you want to do this because you want to get the coefficient of one of the variables to be opposite of the other. So that's the reason why you multiply both sides of an equation by the same non-zero, is to eliminate one of the variables. And then the third rule is to replace any equation in the system by the sum or difference of that equation in a non-zero multiple of any other equation in the system. Okay. So we're now going to apply this to an example. So for this example, we have our system. We have two equations, 1 and 2. We have 4 steps that we're going to walk through in order to solve this system by elimination. Okay. So the first step, we need to multiply both sides of one or both equations by a non-zero constant that the coefficients of one of the variables are additive inverses. Okay, meaning they are the same value, opposite signs. So negative 2 and 2, or 4 and negative 4. Okay. Now, again, there are multiple ways that you could approach this problem, but I recommend going with the clearest pathway to solving your system. What is the clearest pathway? Well, I see here that y in my second equation has a coefficient of 1. So I can multiply 1 by any value so that I then have the additive inverse of negative 2, which is the coefficient of the y variable in the first equation. Because the goal, remember, is to eliminate one of the variables when I add the two equations together. So I want additive inverses of either the y coordinates, the y variables or the x variable. And in this case, I'm going to choose the y variable. So I am going to multiply equation 2 by 2. Okay, so I'm going to multiply equation 2 by 2. So I'll take 2 times the left side and then 2 times the right side. And so now I need to simplify. So when I distribute the 2, I'll have negative 8x plus 2y equals negative 2. So my new system is going to be 3x minus 2y equals negative 3. And then I have negative 8x plus 2y equals negative 2. Okay. So this is equation 1. And so now this is equation 3 because it's now a new equation, but equivalent to equation 2. So next step is to add the equations to eliminate the variable and solve the resulting equation. So I'm going to take my 2 equations from step 1 and I'm going to add them together. Okay. So 3 minus 8 is going to be negative 5. Then negative 2y plus 2y, that's 0, so they cancel out. And then negative 3 minus 2 is negative 5. This gets me x equals 1. Okay. All right. So now we want to back substitute the value of the variable found in step 2 into one of the original equations to find the value of the remaining variable. And that's key. You want to take that variable that you found and substitute it into one of the original. Okay. So since I created an equivalent equation for number 2, I'm going to substitute it into number 1. So equation number 1. So that would be 3x minus 2y equals negative 3. And I'm going to substitute in 1 for x in order to find my other variable. So I have 3 minus 2y equals negative 3. So negative 2y equals negative 6. So y equals 3. So now I have my x coordinate and I have my y coordinate. Okay. So now let's check our solution. So our original equation was 3x minus 2y equals negative 3. Then negative 4x plus y equals negative 1. So in substituting in my x coordinates, negative 4, that's 1. And then my y coordinates, 2, 3. Okay, and then simplify. So this would be 3 minus 6, which equals negative 3. That's correct. And we have negative 4 plus 3, which equals negative 1, and that is correct. So we know our solution then is going to be the point 1, 3. Awesome. All right. Back to our example for movie tickets. So a movie theater sells tickets for $15 each, with senior receiving a discount of $5. One evening, the theater sold 253 tickets and had $3,555 in revenue. How many of each type of ticket were sold? So the first thing we're going to do when presented with a word problem like this is we're going to define our 2 variables. So X is going to represent the number of tickets sold at $15, and Y is going to represent the number of tickets sold at the discount of $5. So in other words, $10. And we found that by taking 15 minus 5, which equals 10. Okay. So now we can write our 2 equations to form our system. Okay. So we have 15x plus 10y equals 3,555. And we have x plus y equals 253. Both of these equations we found in the first example of this section. Okay. So now we're going to solve this system. We're going to determine the number of tickets at $15 that were sold and the number of tickets at $10 that were sold. We're going to do this process by using elimination. So, step 1, remember, is to multiply both sides of one or both of the equations by a non-zero constant so that the coefficients of one of the variables are additive inverses. Okay? So, let's multiply equation 2 by negative 10. That way, we are able to eliminate the y variable. So, negative 10 times the left-hand side and negative 10 times the right-hand side. Simplifying, we get negative 10x minus 10y equals negative 2,530. Okay. So now we have a new system, 15x plus 10y equals 3,555. And we have negative 10x minus 10y equals negative 2,530. So the next step is to add both of these values or equations together so that we can eliminate the additive inverses, which are the 10 and the negative 10. So this will leave us with 5x equals 1,025. Divide both sides by 5, we get 205. So we now know the value for x. So now we can find the value for y. To find the value for y, we want to substitute x into one of the original equations. So the original equation I'm going to use is x plus y equals 253. So that's equation number 2. Okay. So substituting in x, which is 205, I'm going to subtract 205 on both sides, which leaves me with y equals 48. Okay. So that means we had 205 regular tickets and 48 senior tickets were sold. Okay. Awesome. Objective 3. Identify an inconsistent system of linear equations. So previously, we explored consistent systems of equations that had a single solution. Now we will deal with a system that has no solution. So recall these systems are called inconsistent. Okay. So in this next example, we have a system, equations 1 and 2, and we're asked to solve this system. So we will solve it graphically, and we will solve it algebraically. both of which should match together, meaning we should get the same solution whether we do it algebraically or graphically. So for this system, we can either use the elimination method or the substitution method. I am going to use the substitution method for this problem. I could use elimination if I wanted to, but since my coefficients here are rather small and they're all divisible by 2, I know I'll be able to easily use substitution to get my answer. All right, so I am going to take my equation number 2 and I'm going to solve for y. So I'll have 2x minus y equals 4. So minus y equals negative 2x plus 4. Dividing everything by negative 1, I get 2x minus 4 equals y. So then I'm going to take equation number 1 and I'm going to substitute in that expression for y. Let me first write that out for you so you have that. 2y equals 6. So now I have 4x minus 2 times 2x minus 4 equals 6. So I have 4x minus 8 equals 6. 4x minus 4x is 0, so negative 8 equals 6, which is not true. So that means there is no solution. Okay. So that's how we would solve it graphically, where we would get a result that is not true. So that was algebraically. So graphically, we would find the slope-intercept form of both equations and graph it. So I already know the slope-intercept form for equation number 2 because I found it right here. So now let's find the slope-intercept form for equation number 1. Okay. So I'll start off with 4x minus 2y equals 6. So I have negative 2y equals negative 4x plus 6. Divide everything by negative 2, and I'll get 2x minus 3. Okay. So this is the slope-intercept form for equation number 1. Okay. So let's plot our first equation, 2x minus 3. So I'm going to start with my y-intercept, which is minus 3. My slope is 2, so I'll rise 2 and then go over 1. So 1, 2 over 1, 1, 2 over 1, 1, 2 over 1. And then I will connect my dots. And that's for equation 1. Then we can plot equation 2. My y-intercept is negative 4. And my slope is 2. So I'll rise 2 over 1. Rise 2 over 1. Rise 2 over 1. And then I'll connect my dots. Okay. And that's for equation 2. So we see here that graphically, both of these lines do not intersect with each other. Therefore, there's also no solution because there's no intersection point. So writing each equation in slope-intercept form and graphing, we see the lines are parallel, which means the system is inconsistent because there's no point of intersection. Okay. Objective 4. Express the solution of a system of dependent equations containing 2 variables. So Solving a system of dependent equations, we first start off with our system. So we have two equations here in this system. We are either going to utilize the substitution method or the elimination method to solve this system. I am going to use the elimination method to solve this system since we used substitution in the last one. So the variable I want to eliminate is going to be y, because this y term has a coefficient of 1. So I'm going to multiply equation 1 by 2. So I will multiply 2 on the left side and 2 on the right side. Next, I will simplify those sides to get my new equation. Negative 4x plus 2y equals negative 8. So this will be my new equation. So this will be equation 3. So negative 4x plus 2y equals negative 8. It replaces the first equation. And I just want to make this into a bracket. There we go. And then my second equation, 4x minus 2y equals 8. So I'm now going to add both of these together. And you see here that negative 4x and 4x cancel. 2y minus 2y cancel. Negative 8, positive 8 cancels. So I have 0 equals 0, which is true. Okay. So how then would we write our solution? So we can write the solution set using ordered pair notation. Okay. And we can write this in terms of x, or you can write it in terms of y as well. To help us do that, we are going to write our equations in slope-intercept form. Okay, so let's take the first one. So negative 2x plus y equals negative 4. So y equals 2x minus 4. So let's start there. So to write this as an ordered pair, okay, we are going to take our x-coordinate x, and our y-coordinate will be the expression 2x minus 4. Okay. Now we could also write this in terms of y. So we would, in terms of the y-coordinate. So we would get everything in terms of x. So if we were to flip this, we could also have 1/2 y plus 2 equals y. Okay. Either way works. Most of the time, though, in this course, you will write it in terms of x. Okay. Now, writing it as set notation, you would have a squiggly bracket, so x, y, so all the ordered pairs where y equals 2x minus 4, and x is an element of the real numbers. So this would be set notation. Okay. Now you could have taken equation 2, written it in slope-intercept form to get your expression for y, and utilize that in the ordered pair. That's also a solution to your equation as well. But since both of these equations are the same line, if you were to simplify 4x minus 2y equals 8, you would get the same equation. And let's do that. So we have 4x minus 2y equals 8. So minus 2y equals minus 4x plus 8. Divide everything by negative 2. We'll get 2x minus 4. which is the same thing that we got when we wrote our first equation in slope-intercept form. Okay, so it's just another way, excuse me, to prove that both of these equations are the same. So writing the equations in slope-intercept form and graphing, we see that the lines are coincident or on top of each other, which means the system of equations is dependent. Because one equation is a multiple of the other. However, the system is still consistent because there are infinitely many solutions. So we know that both equations simplify or can be rewritten in slope-intercept form as y equals 2x minus 4. So our y-intercept is negative 4. Our slope is 2, so we'll go up 2 over 1, up 2 over 1, up 2 over 1, and then connect our dots. And this would be the line for equation 1 and equation 2.